This week we're going to talk about whether a matrices, whatever, plural, whether a matrix is diagonalizable or not. Now first off, a diagonal matrix is one where there are only numbers in the diagonal. This is really cool because if we want to square it, you just square the diagonal. If you want to cube it, you just cube the diagonal. It's a really nice matrix to play around with. So when can a matrix be diagonalizable? And what does it mean to be diagonalizable? Well, first I need a definition. Always definition. So two matrices, A and B, are similar if and only if there exists an invertible matrix P such that A equals PB P inverse. So let's look at this example. If A is equal to this matrix, B is this, P is this one, and D is that one, you will see that A and D are similar. I'll let you do the calculations. So let's say I want to find a formula for A to the n, where this is my A. I don't want to calculate, that's gross. But if we know that A is equal to PD P inverse, it makes it a little bit easier. So notice, on the next page, if we square it, that means you write it twice. This is a lot of work for something that's pretty straightforward concept. But when you double it, the inner P's cancel, become I, and go away. So A squared is just PD squared, P to the negative 1. So when you have A squared, you'll end up with PD squared P inverse. So if I have A to the n, it will be PD to the n, P inverse. And we already know what PD to the n is. We did that on the previous slide. So if I multiply, wrong way. If I multiply it by P, diagonal matrices are much easier to play around with. Definition. So what does it mean to be diagonalizable? A square matrix A is said to be diagonalizable if A is similar to a diagonal matrix. So that matrix we just played with is diagonalizable. The diagonalizable theorem, that's a pain in the ass to say, diagonalizable. An n by n matrix A is diagonalizable, if and only if A has n linearly independent eigenvectors. Cool. So now think about this. Each eigenvalue has at least one eigenvector. So if you have n different eigenvalues, then you're going to have n different eigenvectors, and they will be linearly independent. Okay, so we're going to do a proof of this only because it helps you see how to find the diagonal matrix and the similar P matrix. So let's go. So assume A is an n by n diagonalizable matrix. And that means A is similar to some diagonal matrix. Let's call it D. And there's an invertible matrix P such that A equals PD P inverse. Or equivalently, AP equals PD. Okay, so we know it is, D is diagonal, and this equation holds. So, I need to talk about eigenvectors. So, let V1, V2, yada, 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 Vn be the columns of P, and the diagonal of D be lambda 1, lambda 2, yada, 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 lambda n. Hopefully you see where this is going. Notice that AP, if I multiply A times P, it's A times each of those vectors. And notice that P times D gives me lambda 1 V1, lambda 2, that should be a V2 there, dot, 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 lambda n Vn. So, and I know that that is equal to that because it's diagonalizable. So the components are equal, which means we have n eigenvalues and n eigenvectors. Since the vectors were the columns of P, which is invertible, that means they have to be linearly independent. So we have n linearly independent eigenvectors. Okay, now, that's what I just said. So let's go the other way. Assume n has n linearly independent eigenvectors. Well, guess what we're going to do? We're going to say, label them V1, V2, up to Vn, and we're going to label the corresponding eigenvalues, lambda 1, lambda 2, yada, 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 lambda n. So, we're going to show that A is similar to a diagonal matrix. Well, D is the diagonal with the lambdas on it, and P is the matrix with V's as columns. And, sorry, cat ran in the way. So we can see that AP equals PD. We're done. So, if we know we have n eigenvectors and n eigenvalues. The diagonal matrix will be the eigenvalues down the diagonal, and the P matrix will be the corresponding eigenvectors. Make sure you know order matters. If you put lambda 1 in the corner, V1 has to be the first one. But if you mix it up, then you have to mix everything up. They have to correspond. So, let's look at this one. Okay. So, what the hell? There should be A. Okay, the possible diagonalize the matrix A equals this. So, we're going to find the eigenvalues and eigenvectors. So, we put our lambda there, find the characteristic equation, we factor. We see the eigenvalues are 1 and -2, and this has multiplicity 2. If we look at 1, this is our matrix. We put it in reduced echelon form. Z equal S, and X will equal S, and Y will equal -S. And there's a typo here. I apologize. That should be -S. So my eigenvector is 1, -1, 1 for the X, the Y, and the Z. Now I need to look at -2. I get, a lot of 3s there. Okay, so I get this for my matrix. Put it in reduced echelon form, I get this. So I've got 2 independent variables, which is good because I wanted 2 vectors. I'm going to let Z equal S and Y equal T, which means X is equal to -S minus T, which means my eigenvector is -S minus T, TS, which when I split it up to do the 2 eigenvectors, I get -1, 0, 1, -1, 1, 0. Which means I know my diagonal matrix is 1, -2, -2, and my corresponding eigenvectors have to be in the same spot. So 1 goes with this first column. The -2s, okay, that doesn't really matter because it's the same thing, go with these second 2 columns. So that's how you find your diagonal matrix and the P. Pretty straightforward to crank these out. Think about what it means though to be diagonalizable, and if you know about certain vectors, certain eigenvalues for a vector, what does that tell you about the matrix itself? Some of the questions are here, crank this shit out. Some of the other ones are, think about this. What does this mean? So good luck. Hopefully when I edit this, it won't be quite so bad.